Hi all. So today we will talk about problem 5.3, leaving the sphere. So this is basically asking for what happens when a small mass is on top of a fixed frictionless sphere. And when this mass is given a tiny kick and slides down, the question asks us at what point does it lose contact with the sphere. So I only drew a hemisphere here since that's all we need, really. So first let's try to do a force analysis. So let me draw a separate diagram, but bigger. So if this is part of the sphere, and if here's the mass, then what forces does it experience? Well, there's a gravitational force and a normal force. There's no friction since it's frictionless. So now it is asking us when it loses contact with the sphere. So a pretty nice thing we can use is that when an object loses contact, the normal force becomes zero. And that's a pretty nice thing we can use. And so let's try to analyze this. So let's try to break the forces down into tangential and radial directions. Because for this sphere to go around this sphere, for this mass to go around this sphere, we need a centripetal force pointing towards, pointing radially. And that's why we want to decompose forces into radial and tangential directions. So let's try to do that. So we need some sort of angle to decompose gravity since it's pointing straight down. So let's call this theta. So this is how much the mass had slid down, and then we call the angle here. So let's say if this is the center of the sphere, so center of sphere, and we call that angle theta. So then how can we decompose gravity? So gravity basically breaks into two directions. So radially, we have g cosine theta, and then tangentially, we have g sine theta. And why is that so? So since this line is the line perpendicular to the this cross area, so we define theta to be the angle measured from this line here that's perpendicular to the cross section of this hemisphere. We know that this is definitely parallel to gravity since gravity points straight down as well. So then this angle must be equal to this angle too. So because there's a line between and these two are parallels, and so that angle must be theta too. And then if we just draw the diagram, we see a right triangle forming here. So since radial direction and tangential direction are always perpendicular, and that's why we define that to be a 90 degrees angle. So it looks like this is gravity, and then you have the radial component, so radial and tangential here. And then we know that this is 90 degrees and this is theta. And that's why we say radial is g cosine theta and tangential is g sine theta. And then we can just write it like mg cosine theta and mg sine theta. M being the mass here. And then after that, what we can do is try to write out an equation for the centripetal force. We know that for the sphere to stay, for the mass to stay on the sphere, we need a centripetal force in the radial direction. So let's see. We know that the radial direction of gravity points towards, so it provides centripetal force, and normal force points opposite to that. And so we can write the equation mg cosine theta minus n equals to mv squared over r. So v being the speed that the mass is sliding down the sphere. And then we said the condition is when n is 0. So let's try to isolate n first. So we have mg cosine theta minus mv squared over r equals to n. And so let's say let n equals to 0, then mg cosine theta must be equal to mv squared r. So 1 mv squared r over r equals to mg cosine theta. That is the threshold when the mass is going to slide down. And so how can we find v? Because really the only unknown is v here, because we can cancel out m. So g cosine theta equals to v squared over r. And remember, we're trying to find theta here, because the question is basically asking us at what point does it lose contact. So we really need a coordinate, and that's theta. So then how can we do that? We just need to find v. So remember here that energy is always conserved. So we know we can get the kinetic energy expression using the gravitational potential energy. So how can we do that? So again, let me draw a diagram here. So I'm just going to draw a hemisphere again. And then we have a mass here. And then that's the center. So imagine this is before it's given a kick. This is the initial point. And then let's say it's here now. And then this is still r, this is still r. So how much has its height changed? So height, changing height basically means this part. This part is the changing height. And so how can we find that? Well, we said this is theta, right? So then all we need to do now is to find the height of this sphere with respect to, let's say, the cross-section of this hemisphere. So this height minus this height. So basically their height to the center. So let's say this is the center. And then you basically want to use this height minus that height. So to do that, we know this height is definitely r. R minus, and if this is theta too. And so this is basically r cosine theta. And this is equal to delta h, and we can factor out the r. We get r1 minus cosine theta equals to delta h. And so what do we know? Well, we know that this is the change in height, and so the change in potential energy equals to mg delta h, which is mg r bracket 1 minus cosine theta. And that is the potential energy lost. And now that we have the expression for the changing potential energy, we know that since energy is always conserved because there's no friction here, whatever this potential energy is lost, it converts to kinetic energy. And so we can write out the formula mgr 1 minus cosine theta equals to half mv squared. And so now we can get v. So let's cancel out m first. And so we have 2gr 1 minus cosine theta equals to v squared. And so v equals to square root 2gr 1 minus cosine theta. And so this is our expression for v. And let's plug that back into the previous formula of g cosine theta equals to v squared over r. So let me rewrite the formula first. So we know g cosine theta equals to v squared over r. And v squared is basically 2gr 1 minus cosine theta over r. And r cancels. And now we have g cosine theta equals to 2g 1 minus cosine theta. And cancel out g. We have cosine theta equals, and expand the bracket, we have 2 minus 2 cosine theta. And then now we have 3 cosine theta equals to 2 theta equals to inverse cosine of 2 over 3. And so theta equals to, so if we draw our calculator, we get theta is about 48.2 degrees. And so this is our answer to this question.